We will get started. Let me introduce Professor Heather Jamieson. Heather's a professor in the Department of Geological Sciences and Geological Engineering at Queen's University, and I guess emerita now. And Heather's won more awards than I can remember, so I won't list them all. For her work in environmental geochemistry, environmental mineralogy, impacts of mining on the environment, and so on and so forth. So over to you, Heather.
Okay, thanks, Matt. And yeah, this is what I've asked to speak about. You've already heard about consequences of mining from Alex. Alex and I both teach in a professional master's program, so we're quite used to working together. That we don't always get to hear each other's lectures. Anyway, let me get started. And I'm going to start by just talking about volume and physical disturbance before we even get to the geochemistry. So this is something I think the general aspects of which you'll be familiar with, but maybe you hadn't thought about it this way. But you know the grade of the kind of deposits you're talking about. And so it's an industry where more than 90% and sometimes more than 99% of the material that's handled is actually discarded. That's waste, different kinds of waste. I'm speaking about the solid material right now, the rock, but we're going to talk about fluids as well. And there's various ways to try to get your mind around this. One way of doing it is that per person in Canada, that's what my statistics are for, we each produce 1 ton of solid waste, the stuff we put at the curb per person per year, compared with 30 tons of mine waste. Now you might say, well, I don't produce 30 tons of mine waste. It's the mining companies that do it, which is correct, but essentially we're part of the story, right? Because we're the people that buy the products and the cars and the computers, etc. On the whole, though, mining occupies less surface area in most places than agricultural things like cropland or pasture, or definitely more than the logging industry. And yet, compared to those, I would say the agricultural ones, which it has a reputation as a dirty industry, possibly deserved. We can think about that and talk about that. But I mean, very basically, can we survive without mining? And I think most of us would say no. But I'm going to, at the end of the lecture, if we have time, try to dig a little deeper into that question. So the photograph shows you something short of 1 million tons of mine tailings. This is on a hill. You have to imagine more of the hill on the right side, but not too much more. I've got about 3/4 of it there. That's a field school I used to teach at, just to get your head around what 1 million tons of mine tailings looks like. It's like 1 million tons of rock. So on a global scale, there have been some interesting recent publications. So here's one where this all comes out of improved satellite imagery. And so here's one that was published fairly recently where they have documented the global mining footprint. Now, when you look at the map of the Earth, these yellow parts coalesce to smudges. It's a little bit, I find, misleading. So some of the enlarged bits below are helpful. On the left, we see the large pit at Escondida in Chile, placer gold and mining. So that's mostly river valleys, and then coal mining in the Ukraine, which sort of coalesces to a smudge on the global map, but is discrete particle areas. And also coal mining in Indonesia. I wish they'd done nickel mining in Indonesia, but that's quite recent. And here's another one that took a different approach. So this group, I've worked with this group, and they're very interested in river systems. So that's what they were focused on. And arguably, river systems are one of the main types of geographic area that are impacted by mining. Not everywhere in Canada, but elsewhere in the world, that's certainly the case, especially mountainous regions. So they mapped river valleys impacted by mining, so it's less comprehensive than the previous study. But the interesting thing is they compared inactive mines with active mines. So the legacy issues when it comes to the environmental consequences of mining are really important. And according to this study, North America, which has the largest, interestingly, according to their analysis, the largest area of river system impacted by metal mining, it's mostly due to inactive mines. And in Asia, it's about half and half. In Africa, it's mostly active mines. You know, I'd like to dig deeper into that kind of information. But the fact that it's inactive mines in North America and Australia does not surprise me one bit. Okay, so what are we talking about? What's
Well, I have a
mine
question.
waste?
I
Oh, a
have a
question. Good,
question.
go ahead.
Yeah, just maybe you're not so familiar with teams, but we raise our hand. But if you go back one,
Yeah,
I'm sort of looking at that massive circle on top of North America and that tiny circle in Asia.
I
That
know.
that kind of surprises me because everybody's hearing about the environmental problems that China seems to ignore. So is this a reporting problem? Is the in Africa? My goodness. Um,
I know. I suspect it is a reporting problem, but I don't have an easy answer to that. So I think I put the full reference, and I think we probably need to dig into that to make sure. I know this group has done a lot of work in Europe and South America and yeah, and Australia for sure, but they're probably looking for other sources. But this is mostly satellite imaging, as I recall. Yeah, it's
yeah,
a really good question. I'm sorry I can't answer it, but
and
I thought that was provocative myself. Yeah.
the funny thing about Australia is it really doesn't have very many rivers, so even more interesting.
Yeah. Yeah. Was there
Anyway,
another
thank you.
question? I see the
Yeah,
hands
John's
going
Yeah,
up,
got one.
but
Well,
okay.
it's John. I'm just wondering what I'm looking at here. I'm not sure. Is it number of river systems, land impacted? What is it? I mean, it just says
It's
100,000.
area. Yeah, it's area. You're right. The units aren't on this figure, which is a little frustrating, but it's a unit pertaining to area.
Okay.
probably
Yeah, so
square
yeah, we got
kilometer.
questions about this paper, and I do too. So all right, I'm going to carry on with the idea that it would be worth investigating this more. Okay, so what are we talking about? Well, we need to consider both solid and liquid. Solid waste, there's a variety of constituents. I'm going to mostly consider waste rock and mine tailings, which I'll talk about in the next two slides. But there's other solids too. Many operations have water treatment facilities, and they produce a solid sludge, which is generally considered to be non-reactive. It's often deposited with tailings. If there's a smelter or a roaster or some kind of processing, either on site, possibly another location, that's another kind of solid waste. And of course, there are gas and dust that's emitted from any hydrometallurgical activity in particular, or there could be dust raised from tailings. So those are all things that should be considered. And liquid waste, effluent refers to what's coming directly from the mill, which or from the operation, usually needs to be managed, either treated or collected in a settling. But then there's also, and we will talk about this in some detail, leachate from waste rock and tailings. By that I mean an aqueous solution that's produced when precipitation or snow melt or runoff interacts with waste rock and tailings. And if they're reactive in some sort of geochemical sense, that leachate can be problematic, can be poor quality. And so the figure on the right sort of depicts some of these components, but it also, I like to include it because it talks about the secondary contamination. So on site, certainly for an operating mine, there are exceedances of both solid and liquid waste that are contained on site and managed. The contamination, what's called secondary contamination in this figure is refers to waters and possibly solids that leave the site. And that's usually where regulations come into effect. Legacy sites or inactive sites are a little bit different. It really depends whether they're managed, have been received any attention, or they're completely abandoned and unremediated. Okay, so what's waste rock? Well, this is the unprocessed rock that was mined underground or open pit. Often, if we're talking about a ore that is sulfide hosted, where the ore minerals are sulfide hosted, the waste rock can be relatively sulfide poor. Sometimes it's pyritic or has non-economic sulfides in it. It's relatively coarse compared to tailings. That's an important distinction. You can have very high volumes, especially from open pits. Depending on how it's managed, it's usually unsaturated. I'm referring to water. So it relatively dry, not completely dry. However, again, through interaction with meteoric water, precipitation or runoff, you can produce, now ARD I haven't defined, that's acid rock drainage. You can produce poor quality drainage of some kind, acid or otherwise. Well, we're going to talk about acid drainage in a minute. So the examples I give, these happen to be from my own collection in Los Frailes in Spain. That was a pyritic massive sulfide deposit. There was a major tailings dam failure there in 1998. You can see the waste rock pile behind the mill there, and you can see the color variation on the surface, which really has to do with the fact that this is a sulfidic, in fact, it's a pyritic ore, and so since the waste rock has been placed there, there's been oxidation and a variety of reactions. And on the right, this is something completely different. This is from a legacy of asbestos mine in southern Quebec. I was just there a few weeks ago, and I was impressed by the fact that these asbestos waste rock piles are actually unremediated, although there hasn't been mining there since late 80s, early 90s, something like that. So as I drove by, I thought I would take a picture of those. They are not chemically reactive, but physically, I mean, they're asbestos. There could be asbestos fibers that would be a concern.
Can I ask a question about that?
Yeah, go for it.
How would you remediate something like that? I mean, cover it with a giant tarpaulin or what?
You would cover it. It would be covered with soil or crushed rock. There are, you're talking about tarps. There are something, and I've done some work on these geosynthetic covers or liners, and they are special polymers that are designed to inhibit hydraulic conductivity. Sometimes there's a kind that we did some experiments that have 2 layers of plastic, the special polymer with clay in between. But if you wanted to cover a pile that size, and this is one of probably 50 in the area, 30, 50, I don't know. That would be very expensive. So you probably go for something like soil and possibly revegetation to hold it in place. Although you never want to revegetate waste rock piles if they're chemically reactive with trees, because the tree roots get down into the reactive material. Okay, just go ahead and say something if I miss your hand up, because they seem to come and go.
Oh.
Okay.
Oh, I was just reminded of when my cousin and her husband decided to minimize their lives and put a lot of junk in the backyard and decided to cover it with concrete. And it took way more concrete than they expected.
Yeah, it's that kind of thing gets expensive. Yeah. Interesting. Huh.
That's
okay.
That's surprising, Clint. I could think about better ways to dispose of stuff.
Yes. Okay, mine tailings. So now we're talking about something that's actually gone literally through the mill. There has been some processing, or flotation, gravity, some kind of separation process to remove the economic, or they've removed most of the economic metal, and it's important that not everything is removed. If it was, we'd have 100% recovery, which would be great, but doesn't usually happen. And so typically mine tailings are silt to sand size, depending on how they're stored, how they're managed. Sometimes, and we're going to get back to this, they can be saturated with water or periodically saturated and unsaturated with water. That could be a conscious decision, like a deliberate decision of management. And we're going to get back to both the advantages and the disadvantages of that kind of decision. Mine tailings, if they have sulfide minerals, can produce acid rock drainage, but it doesn't necessarily need to be acid to be poor quality drainage. And we're talking about things that could be high in metals. If tailings are dry, they can produce dust, which again could be high in metals and problematic. So managing solid mine waste at an operation is usually managing the waste rock. That tends to be fairly simple, piles, covered or unpiles, depending on what kind of problems there are with them. And mine tailings, which are a little bit more complicated, because they're finer, they're more reactive. And they also tend to migrate more easily as particles. So in the left, there are something which I was asked not to call tailings, but they are tailings because the diamond mines in Canada like to refer to their processed fines. But that's the end product of the processing at a Caddy diamond mine. The diamonds have been mostly removed, and so it's basically crushed kimberlite. In fact, these tailings, when they're dry and you look at them closely, are, to be honest, from the point of view of a geologist or mineralogist, quite beautiful because you have green olivines like peridot, and you have chrome diopside that's black, and you have very nice garnets, pyropian garnets, dark purple. Anyway, on the right, you see tailings from a massive sulfide mine in northern Ontario. And I like this picture because if you look at the lower left, can you see my cursor?
Yes.
Good. In the lower left, you see the pipe that's spilling the tailings. At the time I took this photograph, the tailings are black. They have quite high sulfide content in them. Verging on 20%, as I recall. And at the back, you could, but they're fresh tailings, and at the back, you can see some orange tailings. You can actually sort of see that there's dust being raised from them. So those are oxidized tailings. And this was, it doesn't look like this now. This operation has been closed for quite a number of years, and these tailings are all covered. Okay, and just looking ahead, well, what do we mean by the impact? Well, there's a big focus, certainly in Canadian legislation, on aquatic impact, aquatic life, fish and fish habitat. And that's focused on the damage outside the mine property. They talk about the point or points at which the water leaves the property. That's where the rules come in. And the legislation that really is most, how would I say it, impactful maybe in Canada is under the Fisheries Act. I actually know the person who wrote that legislation. He had a degree in metallurgy and a degree in law from Queen's, and he owned a property on which I used to teach my field school. And I asked him once, well, why is it in the Fisheries Act? Because there's more than fish and fish habitat. impacted from mining. But he said at the time that it was written in the early 70s, there was Environment Canada had just opened up. Most of the provinces did not have environment departments, and it was felt that the Fisheries Act was where they need to put something that had teeth in it. Human impact, and you've been listening to Alex talk about social impact in a broader way than I'm certainly going to talk about it, but human health impact is it less common? Probably overall, but it also receives less attention, I think, is what I'd say, with exceptional cases. And usually the interaction between humans and mine waste is through poor quality water or possibly dust. So the photograph you see in the upper right is just back at that mine in Northern Ontario, where prior to their remediation, water was escaping the tailings and getting into the local creek. And you can see there's been some kill of the trees there. And that red, we'll get specific about that, but the red coloration is basically due to the acid rock drainage series of reactions that produce iron oxyhydroxide minerals, and that's what gives it the red color, and the suspension in the water makes the water look red too. On the lower right are some gold mine tailings in Nova Scotia. They're not acid, but they're extremely high in arsenic. And I think we took that picture about 2006, maybe. These are just behind a community. It's not remote. It's a half an hour from Halifax. And we were collecting dust samples with the equipment shown there. And these are some kids riding their dirt bikes, which was very common in that area, and despite the medical officer of health putting up signs. And I'm really happy, but I'm sorry it took so long that only this year is the government of Nova Scotia actually covering these tailings. Okay, well, let's talk more and with more scrutiny about acid rock drainage, and sometimes called acid mine drainage. But the mining industry, and with justification, I think, prefers this term, because you can get acid rock drainage on road cuts or in gravel pits. It doesn't have to be a mine. It's usually considered the most serious environmental problem, and you might think of that as the most expensive. Ongoing. I remember being at some of Barrick gold mines in Peru, and they had quite a serious problem with acid drainage. And I was told that they would have to treat the water basically forever. So if you're running water treatment plants per year, they may not cost that much, but if you're running them forever, that's a very expensive remediation effort. It's critical in permitting to operate or close mines. You can't open a mine these days without having a closure plan, and the closure plan, if there is, it has to tell you whether there is going to be ARD. We're going to talk about prediction in a minute. And if so, how it's going to be controlled. And it results in many cases, not all, but for most minerals and metals in minerals, it results in leaching into water, increased concentrations in water of things like copper, zinc, nickel. And so practitioners, people in the world of environmental geochemistry, working on permitting and working for mining companies or consulting companies, usually always refer to ARDML, acid rock drainage / metal leaching. And one of the reasons that's important is you can have non-acid, poor quality waters. I'm not going to go into the chemistry of this in detail, but there are some elements. Arsenic is one of them, nickel, zinc, molybdenum, selenium, others. They can reach concentrations through metal leaching under non-acid conditions that are problematic. Nova Scotia is a place, again, you don't usually see the reddish color when you don't have acid. It's a bit of a telltale, and those are very arsenic rich legacy gold tailings. And the one on the right is a massive sulfide ore, and it's got enough carbonate in it that it actually neutralizes the water, but that isn't always the case, and we will see an example. There's two, just to further this idea that not all poor quality drainage is acid, I can describe two of the most expensive mine remediation projects in Canada. Now, this is a little disingenuous because those costs, those mines are both being owned and managed. They're abandoned and they're owned and managed by the Canadian government. So those costs are publicly available because it's a government owned. The remediation costs of many other privately held or mining company held properties are not publicly available. So that's just a qualification. So the Faro mine in Yukon was a lead zinc mine. It's got large quantities of tailings and particularly waste rock, huge piles as you drive by. It does have acid leaching. Zinc, copper, and lead are problematic. And there's lots of work going in, lots of mining companies, university researchers working here. And the estimated cost of remediation, according to our federal government, is $2.4 billion. And the Yukon is a territory, not a province, which is one of the reasons it's managed by the federal government. The other one is in the Northwest Territories, also not a province, and that's Giant Mine. And here the cost of remediation is $4.38 billion. That's really a lot of money. But there's no acid mine drainage. It's a gold mine, quite a large gold mine, operated for 50 years, went bankrupt in 1999, was taken over by the federal government. It's relatively low sulfide, but there's quite a lot of arsenopyrite, so it's an arsenic problem. There is dolomite in the ore, and so what sulfide oxidation occurs is neutralized by that dolomite. But there's big problems with arsenic. It's dispersed in the property. So I should tell you, I've been doing research, giant mines since 1999, and I'm actually on the board of directors of the Giant Mine Oversight Board. So it's a big part of my life. The stack emissions, you can see the old roasters. So they had to roast the ore to liberate the gold, to make it amenable to cyanidation. So that's a roaster operating in the early years. They had no pollution control. So we're talking about 1948 to 1952 or so. And that stack emitted 20,000 tons of arsenic trioxide up to 40 kilometers away. I can still see it in the soil. But after that, they put in pollution controls. They captured the arsenic trioxide, which is highly toxic, and they buried it underground. So that's their other problem.
Heather, Bob's got a question.
Yeah, go ahead.
Thanks. Now the arsenic, was that from the ore or was that brought in for processing?
No, that's from the ore, and I can clarify that, but the gold was included in the arsenopyrite. So it's one of, Matt, did you talk about this kind of mineralization, sometimes called lode gold?
We have talked about different styles of mineralization. I forget how much we talked about arsenopyrite, though.
Yeah, so quartz carbonate veins, and arsenopyrite is really the host for the gold. So they can't just cyanide it. It's not, it's called refractory gold. They have to do something to it, and roasting, which means heating it up to about 500 degrees in oxygen, it's still one of the main ways to do this. And if you do that, your arsenopyrite kind of breaks down and the arsenic goes up the stack, as does the sulfur, as SO2 goes up the stack, and you're left with this kind of spongy iron oxide mineral, but you can treat that with cyanide and get out the gold. So yeah, the arsenic was not brought in. Yeah.
Okay, yeah. So this comes to mind because one of our students is going to be working on a project on the Carlin, where I believe there's a lot of arsenopyrite there, and maybe that's going to be a topic of interest.
Heather,
Okay.
do you remember off the top of your head what the value of the gold they extracted from Giant Mine was?
Well, it depends what price of gold you use, right?
Well,
If you looked at it now, it'd be totally different. But I think the paper that was published in the 90s put it at, no, I don't want to say a number in case I'm wrong, but 2 million? That's what I'm,
2 billion?
most of this was a rich mine, but most of the gold was produced at the time that the price of gold was quite low.
Yeah. So the cost is more than the value of the gold, or on par anyway.
Yes, now that there was a paper that I referred to where they tried to do just that, Matt. They tried to compare the value of the ore that was produced to the cost of remediation. But, we've discussed that a lot, and that feel that's an oversimplistic.
Sure.
The value could be enhanced by saying so that the city of Yellowknife, 20,000 people, didn't exist before this mine, and there were two mines actually, another one equally large, existed. So one could say hospitals, schools,
Sure. Yeah.
all those things were brought in because of the gold mines. That could be put on the value side, but on the cost side, you could say that the concern of the community, possible, it's being tested now, health impacts, things like that. I had this conversation once with someone in Yellowknife. I spent quite a lot of time there, and they said, well, thank you, but we didn't really want those hospitals and schools at this cost. So yeah, you can compare the numbers, but I think it's kind of oversimplified.
Sure. Thanks.
Anything else? I can talk about Giant for an hour, but I think I better go on. Okay. All right, so let's do a little bit of chemistry. So acid drainage is rooted in the oxidation of sulfides. And that's, you could write this equation different ways, but a good way to write it, in my mind, is to use pyrite and molecular oxygen, water, and you end up with an iron oxyhydroxide mineral that's very hydrite and dissolved sulfate and a whole lot of acid in the form of hydrogen ions on the right side. Now, you do get some dissolved iron as well, and sometimes if there's any calcium around, you tend to precipitate the sulfate as gypsum. We'll see an example of that. But that's the basic thing. And it's written for pyrite, but other sulfides oxidize, and you could write equations for pyrrhotite, chalcopyrite, and then you would see copper being released and sphalerite, zinc, iron, cadmium kind of disappeared there. Cadmium can be a trace component in sphalerite, but it tends to be potentially more toxic than the zinc or the iron. So I wanted to include that. So then the other important group of reactions is acid neutralization reactions, or something that consumes those hydrogen ions, and that tends to be carbonate. In ores and mine waste material and waste rock and in tailings. And there's a simple equation to describe that. You end up with, on the right-hand side of the equation, with dissolved calcium and bicarbonate. Calcite is quite effective at doing this. Dolomite is a little bit slower, but it can be effective. And talking about time, when we were thinking about geological time, and now we're thinking about processes happening at the surface of the earth. When I say it's slower, I'm talking about reactions that are not in minutes, but more in days or weeks. Importantly, iron carbonate, and that's ferrous iron carbonate, siderite or siderite, is not an acid, or the net result of dissolving iron carbonate is not to consume acid, but actually to produce more acid. So iron carbonate is not a good kind of carbonate, so to speak, to have in your ore. Okay, so I want to talk about prediction, specifically what tools are used to predict whether a given mine waste material, be it waste rock or tailings, is going to produce acid. And many of my former students, this is they work for environmental consulting companies. This is what they do. It's a really important part of the exercise. It's critical to getting permits, and those permits can apply to opening a mine, closing a mine, expanding a mine, many things. Even building a road, building pipelines. They do tests for to answer this very question: will the waste generate acid? If we leave it around exposed to the atmosphere and the hydrosphere, what's going to happen? When is it going to happen? What metals are going to be leached? If it's something that I mentioned cadmium. So cadmium, if you look at the legislation or the guidelines for cadmium in water, it's very low. So I mean, the maximum amount is very low. So that would be something that selenium's another one. So these have to be done preferably early, and there's 2 tests that are commonly used. So these have been around for quite a long time. One is called static tests. And what they do, and the specific one we'll look at is acid-base accounting, is they provide a snapshot of whether this solid material you have, this waste rock or tailings, has a tendency to produce acid. Okay, but the kinetic tests, which should be number 2, are column field bins. I'll show you some examples of each that simulate weathering. So they're going to answer the second question up there, or if they're done properly, they will tend to answer that. How long will it take to go acid, or will it be acid immediately? So let's go through these. But the first question, and I talked to some practitioners in the field, and they say that this can't be overemphasized, is what are you going to test? What's going to be waste if you're at the very beginning of a mine or a mine expansion? And so this is actually a real example, but it's a cross section. The ore body's a little hard to see, so I put an arrow to it. Don't worry about knowing what the other rock types are. We're just trying to decide what are we going to test. And basically anything that's going to be excavated and anything that's going to be so that includes the overburden and the host rocks, or broader, if you're going to make an open pit, which was the case here, what realistically is going to be incorporated in that or exposed in that open pit. And then anything used for remediation also needs to be tested. And I've seen an example of that where a soil cover was I guess it was purchased anyway. It was brought to a mine site. This was in Montana, and then they tested it, and it turned out that the soil itself had some sulfide minerals in it, and it was going to produce acid, so it had to be rejected. So we're talking about a large number of samples, and further on, I'm going to show you how much that costs. Okay, so acid-base accounting is really accounting. This is the way it works. Basically, you calculate and compare the acid potential and the neutralization potential. Normally, this is done in the lab. You can do it other ways, but normally it's done lab testing. There are companies that will do this. Generally, there's commercial company is what's used by mining companies and consultants. So AP is the acid potential, and that's normally determined by measuring the amount of solid sulfur. And the calculation assumes it's pyrite, and it makes surprisingly little difference, even if it is not pyrite. But what is important is to do an analysis that distinguishes sulfide sulfur, which will tend to oxidize, as shown. This is slightly different from the equation I showed before. Sulfate sulfur, which is already oxidized, like if you had gypsum or barium sulfates or something else in your rock, that's not going to contribute to acid potential, so you don't want to count it. and organic sulfur, which is generally considered not to contribute, but sometimes it's ambiguous. Okay, then you have the NP, which is the neutralization potential. And the easiest way to measure this, the way it's done in past years, there were some more complicated ways to do it, but generally they measure the total inorganic carbon and assume this represents calcite. Now, I've already mentioned that dolomite is okay but slow, and siderite, iron carbonate does not neutralize. So ideally, some mineralogy would inform the NP determination better. And then they're compared. NP over AP is a neutralization potential ratio. And if it's less than 1, obviously you have too much sulfide, too much acid potential, and those materials are labeled PAG, or potentially acid generating. And if it's greater than 2, then acid generation is considered unlikely, and those materials are labeled as NAG, or non-acid generating. And between 1 and 2, there's ambiguous or indeterminate. You don't know which way they're going to go. So this is very common tool. Doesn't tell us anything about rates or time, but it's a very common tool to characterize materials. So let me show you some examples. Oh yes, I had to say that these tests can also be done, because it's something that we do quite a bit in our research program, using automated mineralogy. All you need to measure all the area occupied by the sulfides, the area occupied by the carbonates. You get lots of extra information because you know what sulfides and what carbonates you have. But typically it's done in a lab. Okay, so this is an example from a mine plan proposal that I was recently involved with. And what they're plotting here, what we plotted for some tailings that we created in the mining department at Queen's. This is a proposed mine, or 2 mines actually. We created those tailings, and then we have plotted the acid potential against the neutralization potential. So the background here is a company called Fireweed Metals. It owns a SEDEX deposit. I expect you've heard about those, the lead zinc silver deposit. It recently acquired a nearby skarn-hosted tungsten deposit. And the mining company, Fireweed, proposed in one of their early plans to mix the tailings, with the idea that, hey, it's a skarn, it has lots of calcite, and that could neutralize the sulfide minerals, which, because the SEDEX deposit was sulfitic, and actually the carbonate it had was mostly siderite. I was able to tell them that with a little testing. And so a former PhD student of mine, Ali Surratt, created these tailings by doing flotation in the labs in the mining department here, and tried mixing them. And then she measured the acid potential and the neutralization potential to see what happened. So here's the tailings from the SEDEX deposit, and they're above this line, which represents an NPR of 1, or neutralization potential ratio. So they're potentially acid generating. Everything above that line is a PAG material. So we weren't surprised that these would be. Here are tailings from the skarn tungsten deposit, but yes, it has a lot of calcite, but it also has a lot of pyrrhotite, or iron sulfide. So in fact, those are also PAG materials. So if you mix them, well, not surprisingly, you're still above the line. So in fact, we are able to tell Fireweed that this isn't going to be a magic solution. So they're going to have to think about something else, which they are. Here's another example at the left for the Pebble mine in Alaska, or the Pebble deposit in Alaska, unmined deposit. And I like to show this one. Now, first of all, I have to tell you, let me just check. Yeah, for some reason, this one has acid potential on the vertical axis, and this one has NP. Ugh. Okay, well, that's a little frustrating, but just remember the potentially acid generation, or the bad rocks, are down here. and the ones that are, they call them acid consuming, this is from the USGS, are up here. And the reason I like this example is because we're not given all the details, but they're plotting. First of all, you can see how many samples they took. So this was an exploration company that did this, or they're environmental consultants. And so there's many samples and there are many different rock types, but just in this diagram, they do separate them by age. And now the geologists know that, okay, the tertiary rocks are okay. They're not going to produce acid, but everything else is or is uncertain. So there's a lot of information gained by that when it's in early stages. And this is from a different area, and I'm sorry I couldn't retrieve the name of this mine that developed this plan, but here's some prospective open pits, and they did enough testing. These were from drill holes that were then projected onto prospective open pits that they could map the PEG materials. So those are the potentially acid generation, the problematic ones, and the blue, which are acid consuming or non-acid generating, and then the ones in between. Okay, so those are examples. Now we're moving on to kinetic tests. So now this is more complicated, but ultimately valuable, because now we're going to get something about time, something about weathering rates. And this is done in the lab by mimicking natural weathering. So in the upper right, you see, whoops, you can see a lab setup. This is very typical. You have about 1 kilogram or so of crushed material, whether it's potential waste rock, they still crush it quite fine, or tailings, and they create rain, so to be run through water for 3 days, and then they dry for 3 days, and they test on the 7th day. That's typically the way they do it. So you can see the fluid being gathered here. And these are run for a long time. Many people think, decision makers think you need 2 years of data. So you can see how challenging this is for a company that's trying to bring something into production. Even more informative in some ways are what's shown here in the middle, these field bins. And so the material now, you've got higher volume, it's in some of these bins, there's a collection system underneath. And the main difference is this is exposed to real weather on site. Even more elaborate, and this is from the field bins, I'm not sure where they're from, but the waste rock piles are from Antamina Tech's operation in Peru. And these are huge piles. You can see a vehicle here, a front-end loader, for comparison of different waste rock that they are producing. And these have been instrumented, so they're collecting water at the bottom and testing it, and they're getting some idea of the kinetic behavior of these materials. And the kind of information you get is shown in the lower right here. This is for 3 samples of different amounts of sulfur. pH and dissolved sulfate is plotted, and not surprisingly, the sample with the highest amount of sulfur produces the most sulfate and also has the lowest pH. So it's got the highest amount of oxidizing sulfide minerals. And this is shown for quite a bit longer than 2 years. This is a academic paper. What you're looking for is a plateau. So you can see if you did the test too soon, you get something that certainly for the pH, which doesn't necessarily represent any sort of plateau. It's arguable what's happening with the sulfate here, sort of a plateau. But there's a lot of information that can come from these. Okay, and here's just some idea of costs, and Matt could correct me if these are, sometimes they have to be, they usually are increased, the costs and the turnaround, But again, this is a reality check for especially junior mining companies, some which don't have that much experience, and suddenly realize, oh, now they're going to have to do some kinetic tests that are going to take weeks or years and cost thousands or tens of thousands of dollars before they can apply for a permit. Okay. I assume there's no questions, so I'm going to go on. We're going to switch a little bit and talk about prevention and remediation. So prevention meaning if you're anticipating having a waste material that's going to produce problematic leachate, what can you do to prevent that as much as possible? Remediation is more in hindsight, obviously, but it's all too common. And the way I've approached this is to think about what's needed, what actually creates acid rock drainage. So if we think about these 5 things that are needed for acid rock drainage to develop, can you eliminate one or more of these and prevent it? Okay, so sulfide minerals. Well, if you've got, we'll talk about an example, but obviously if you've got a non-sulfide ore, things are much different. But many of our ore deposits are sulfide based, not only the ore minerals, but the accompanying gangue minerals. Oxygen, needed for reaction. Water, needed for reaction. What I've awkwardly called an absence of carbonate, because if you have enough carbonate, you're not going to have ARD. And I've added time. Some people have put in bacteria because a lot of these geochemical reactions are driven by bacteria, but you can't really eliminate bacteria because they're ubiquitous. These are sulfide oxidizers, iron oxidizers. They're very common in the environment, so I didn't include them. All right, and so an example here is from a project that Matt and I did in collaboration, and we had a student, Brent Casamel, who's shown down here, taking a water sample. And this is it's a different tungsten mine, although it's close by to the one I referred to earlier. And Brent looked at tailings from 2 parts of this mine. In most of the tailings are in these impoundments that you can see up here in the upper photograph. And when he measured the water and it's near neutral, he looked at the minerals, and this is pretty well the primary minerals. So you have scheelite is the ore mineral. Of course, it's there. It's still there in the tailings, not too much of it. But you have carbonates, you have both calcite and dolomite, and you have a sulfide, you have pyrrhotite. And you can't tell by just looking at the pie chart whether you've got enough calcite to take care of that pyrrhotite if it oxidizes or not, or enough calcite plus dolomite. It's a more complicated calculation. And then on the other side, you have a bunch of silicates, which honestly don't play as big a role. Now, this area where he's sampling, which is quite close by, is where in the early days of mining, they dumped the tailings. They just put them on the edge of the river. You can kind of see this is actually quite a big river in the back, the flat river. And they dumped these tailings, and yes, they have been oxidizing. And the pH of the water that Brent collected was as low as 2, although I think that sample was closer to 4. You can see the iron oxide colloidal there in the water. And when you look at the minerals, it's such a classic story of sulfide oxidation to secondary minerals. The sulfides are pretty well gone. We've got 0.25% of the total. The carbonates are pretty well gone because they were used up in neutralizing those sulfides. And now what we have are sulfates. We have gypsum and iron oxides, goethite. And that's a story of acid rock drainage mineralogically. Jarosite, which is interesting, still have a little bit of scheelite, and the silicates are fairly passive. So here's my question for you. Why don't we have acid rock drainage developed here in these impounded tailings? If you look at these 5 things, is there one or more of those that's been eliminated? So I'm asking if anybody has some guesses.
The carbonate. Is carbonate in?
Well, there is carbonate up here. There's calcite and dolomite. So I'm asking why this hasn't gone acid up here. I mean, maybe I wasn't really clear.
Oh, okay.
Yeah, so why it's sitting here? It's been sitting here for some years, but it hasn't gone acid, and there hasn't been this reaction that produced that eliminated the sulfides and the carbonates. Any other ideas?
Is it dry?
Is it dry? So this is a good question. It's kind of damp. This is not unlike some tailings dams. This one's designed to be semi-permeable, so the water can leak through. Whether that's a right or wrong design, that is the way they did it. So you can't really see in this photograph. Sometimes there's water on top and sometimes there isn't. So you're thinking about water being the thing that maybe yeah, but how would water prevent acid rock drainage?
If there's no water, then there's nothing to drain.
There's nothing to drain, you're right. So there is some water. You're right. You're absolutely right. So if it was bone dry, I would say, okay, water's our candidate. And by the way, this isn't a simple answer because we're still scratching our heads over this one. Any other
But,
ideas?
but there's so
Are
much
there
calcite.
microbes
Is it?
using up the oxygen?
I'm sorry, what did you say? Something about oxygen?
I was asking if there's like aerobic respiration by microorganisms using up all the oxygen.
I think oxygen is a good one. I'm not sure if we understand the process. There's so little carbon in these materials. We know we have some microbes, but we don't know what we have. It hasn't been studied. But I think there's relatively little oxygen here, certainly in the deeper areas, and that's probably has something to do with it.
Yeah, they're fine grained, right? The tailings, so
They're
it's hard
quite
for the
fine
oxygen.
grained. Yeah,
It's hard for the oxygen to diffuse very
yeah,
far
you're right.
downward.
It's
Yeah.
not like a waste rock pile where you have coarse things.
Yeah.
So I think oxygen is part of it, but the other thing that might be is time. And the rather frustrating thing is that there's been very little this mining company that owned this deposit for a long time didn't spend a lot of money. They were a small company. They didn't spend a lot of money on environmental testing. So there was one kinetic test that was done in a lab, and it predicted that it would take 18 years before this material, it has been, no, actually, this is only about 12 years, but some of the other impounded tailings are 18 years. But one sample is not enough. So it's a tough one. But we think it's probably a combination of the limited oxygen and time. So I'd like to show some active measures taken to and in this model of how can we remove some of these 5 things. So how can you remove sulfide minerals from tailings? Well, that would be pretty difficult and expensive, especially if you're looking at a legacy site. But I did see some interesting examples at one of Xstrata's nickel mines in Sudbury, Strathcona, I think it was, because they had some tailings that were acid generating, these reddish material here. So those are the PAG materials, and they had others that were non-acid generating. It was mineralogically complex area. So what they did was separate them, which was somewhat elaborate, and then use the NAG tailings as a cover on the PAG tailings. And on the right, you can see that eventually, this is an area that's been remediated earlier. They put a little bit of soil and some fertilizer, and they actually grow vegetation. So that was quite successful. They had to retool their mill to do this. Here's a way that oxygen is removed. Now, in this example is rather dramatic to look at because it's a case. It's in Elliott Lake, Ontario, so it's uranium mine. And the uranium deposits have pyrite in them. So they had oxidation. You can see the discoloration here. And so what they did was simply raise the dams to deepen the water cover. So that didn't reverse this oxidation, but it prevented more. More commonly, and we're going to talk about that near the end of the lecture, more commonly, from the very beginning, tailings are put in an impoundment and covered with water. They sometimes call that a wet cover to prevent oxygen ingress. Those ones I showed you at the tungsten mine were a little unusual. What about removing water? Well, this has become more important recently, mainly because there's been some serious tailings dam failures. And so you could do this with a dry cover. I've seen this done sometimes in mountainous regions, and preferably low hydraulic conductivity. We're talking about the tarps, maybe some kind of capillary barrier. Can get very expensive very quickly if you've got large areas. But another thing that's become quite popular is filtered tailings. So removing the water from tailings before they're deposited. They're sometimes called dry stack tailings or dry stacking, although the industry doesn't like that because they're not perfectly dry. It's true. They're damp, but they don't require a dam to hold them back. They don't require impoundment with a constructed dam. And that's very attractive, especially, as I said, in the face of recent tailings dam failures. It used to be only used in Saudi Arabia or places like northern Chile where it's very dry. But here's an example in Canada, in the Meliadine gold mine in Nunavut, Agnico Eagle's mine, where they are dry stacking or filtering their tailings as they come out of the mill. So you have to have another piece at the mill, big filter presses. It's not something to do retroactively with ease, but they're doing that in a place that's not particularly dry climate.
Bob's got a question.
Yeah,
so
go ahead.
So what is the purpose of putting it in piles before you dispose of it? I mean, it's not going to react, right? But when you
like
put
in
it in a big
Lycopia?
pile, won't it start to react?
Well, the idea here is, yeah, I'm glad you said that, because that if there is enough sulfide that's fine grained, that is appropriately reactive, even with only a little bit of water, you can get reaction and you can generate a poor quality water. So I'm not too sure whether they're doing this at Meliadine. I know who took this picture, so I can ask. But sometimes they're still collecting water and treating it. Okay. But the idea is that this is better than having a tailings dam that you have to maintain, and the amount of water they have to treat, because the tailings are almost dry, is relatively low in volume. Does that help? Does that answer it? If you're asking why at Lycopia they have them in these individual piles, I do not know. I think those are just, I think they're just dumping them there and eventually smoothing them out.
Okay, thanks.
Yeah, I didn't take that picture, so I'm not sure. Okay, then absence of calcite. Well, you can add calcite, or sometimes lime, calcium oxide is added directly to the tailings, or more commonly in water treatment. So that's pretty simple. And then time. So this is tricky because, operators and decision makers really need to know whether you're going to have something react very quickly, or you're going to have time to build, to construct, design and construct an appropriate tailing storage place. And so before things tend to go acid. So prediction is important, but prediction is the basis of the best design, and doing something incrementally, not waiting until closure is generally the way things are done now. It's no longer considered acceptable to deal with your mine waste only when the mine closes. Okay, water treatment. Water treatment is very common, whether or not you use any of the techniques that are described in the previous slides. The very basic for sulfidic acid producing material is the addition of limes or calcium oxide or slaked lime, which is calcium hydroxide. It produces gypsum and iron oxyhydroxides, just what our students saw in the naturally oxidized or naturally oxidized material. Tends to have a fair amount of metal in it, but it's considered fairly stable. And these two pictures at the top are from Northern California, from Iron Mountain, which is a place I worked on with some USGS colleagues some years ago. It's a very interesting mine drainage because the pH is between 0 and 1, and they have collected waters in some area that actually have a negative pH. So it's extremely acid water and treated the same way any acid water is normally treated by, you see the silos with the lime, and here's some of the sludge in one of these reactors. And then they truck the sludge up the mountain and put it in an open pit. Another kind of water treatment, a little less common, is to use some kind of bacteria. And in this case, we're looking for sulfate reducing bacteria. It's kind of like turning the sulfide oxidation equation backwards. So if you can use these bacteria to reduce metal sulfates to metal sulfides, then they can be collected and stored. And this can be done in tanks like this, bioreactors, or it actually will occur in an engineered wetland. Well, that's what we would call a passive treatment. Okay, so impounding tailings with water covers is the most popular method in Canada. In most mines, that has been historic. It's still the case, but that really depends on the stability of the dams. And of course, this is long-term monitoring and maintenance of the dams. And this is a very large tailings impoundment. In fact, it's only one of several dams in this impoundment at Highland Valley Copper in British Columbia. And of course, the difficulty is that dams fail. This is also British Columbia. This is Mount Polley. This was taken shortly after the tailings dam failure in 2014. So you can see the breach here, and they've also put in a dam here to hold back. The water's all gone. It went down a creek and into the Canal Lake, but they're holding back the solids until they can do further remediation. It's an interesting case study because the tailings were not acid, but there were some high copper values there. It's a copper gold mine. And the company itself paid, I think, $70 million to do the remediation. But interestingly, they survived as a company. Unfortunately, tailings dam failures are not uncommon. So here's one of I've got this information from this website. It's an Australian website, but I've been very selective. I've only chosen to document or to list tailings dam failures in which there was substantial damage, particularly human fatalities. There are many that are much smaller. They may close operations. They may pollute part of a river or damage some fish habitat. But if you look at the website, you can see that every few months there's a tailings dam failure. These are not rare. There are some very large ones. This one in Brazil, I say more than 270 killed, but in fact, I've heard an update. It's over 300. Most of them were people working at the mine. It failed. This is a photograph from downstream. It was an iron mine, not acid. The material is a bright pinkish red. Quite bizarre in some ways, and it happened during the day, which made a difference. And many of the workers were in the lunchroom, which was right downstream from the tailings impoundment that failed, and that's how they were killed. There's Mount Polley I talked about in 2014. There's one in Spain. I also worked on this one in where there was a lot of flooding, but it happened. Both Mount Polley and Los Frailes both happened in the middle of the night, and that made a difference because people weren't out and about either at the property or downstream. Okay. Oh, I've given a link to a video here, and I would show it, but I've often had trouble showing it. But it's a minute long, and it's taken from the security cameras at the Brumadinho mine in Brazil, and it's really quite spectacular what they caught of the failure and the subsequent slide into the mine property. So I thought maybe we can discuss any aspect of this lecture or anything else I can contribute to if you like, but I thought maybe we could start by thinking broadly. So one of my colleagues in Yellowknife talks about mining, or I guess he's thinking about a mine permit. He calls it a license to pollute. That's what mining is. He says it's a license to pollute, and which is a harsh thing, but I don't think it's entirely wrong. So here we have these environmental consequences. You've heard from Alex about some of the social and human consequences. So maybe we can think about how we can do things differently. And I just put up some big ideas that would need a whole lot of expansion. And I wondered if anybody had something to contribute. Now, I would really like